This video will be a review of Taylor series in mathematics. So let's say we have some general function of x, f of x. It can be as complicated as we want it to be. So let's say we have this graph over here. This looks like the graph of, say, like e to the minus x. Okay, so e to the minus x might be fairly complicated to evaluate. Maybe if you don't have a calculator around, could be difficult. Maybe you just want some approximation in some small region. So these functions in general could be complicated, but polynomial functions are simple. So if we want to approximate this function near some value here, like let's say we have around the value x naught, we're interested in the values of e to the x or e to the minus x around x naught, then we want some way to approximate those with polynomials. So the first approximation we could do is just say that the value there is just the value at x naught, just f naught. Or we might get more sophisticated than that and say, well, let's approximate it as a linear function. Okay, so it's going to be a linear function there, but then as the further we get away, the worse an approximation that gets. So we could say, well, let's approximate it as a quadratic function and take into account the curvature of the function as well. Then that would be a better approximation for longer, but eventually that would decay away as well. So we want some kind of function of arbitrary accuracy, depending on how accurate we want things around this particular point here for our approximation. So we're basically building up here to have a function which is defined as a series of polynomials of increasing order as we go. But we need these coefficients, so we need what the linear coefficient is, what the quadratic coefficient is, the constant coefficient. We need to find what all these coefficients are. So how do we do that? And the answer is going to be through using derivatives. So we're going to define a Taylor series as a function which we can define as a sum from n equals 0 to infinity of 1 over n factorial of the nth derivative of f of x evaluated at x equals x naught times x minus x naught to the n. Okay, so we'll see that basing our function around x naught, our coefficients we're going to get by the nth derivative of f of x at that particular point. Now this might seem kind of abstract and odd to go about this, especially if we do know a function exactly like e to the x, but there are going to be cases where we either don't know the function exactly or we need to do things to the function that are hard to do to a function in general, but are really easy to do for polynomials. So there'll be many cases in physical chemistry where we want to approximate things around a small region that are very complicated, but are pretty simple if we just do it around that immediate region and make our lives a lot easier. Okay, so this is the definition of a Taylor series. So this is going to end up being f of x equals f of x naught. So the first term, just the a is the value at x naught. Makes sense. Plus the derivative at x equals x naught times x minus x naught. So 1 over 1 factorial is 1. 1 over 0 factorial is 1 as well. Plus the second derivative at x equals x naught. Actually 1/2 of that. 1 over 2 factorial is 1/2 times x minus x naught squared plus, and then it continues beyond that. 1 over 6 times the third derivative at x equals x naught times x minus x naught to the third, and so on. It goes beyond that. Okay, so let's do an example. Let's do the example of f of x equals e to the minus x minus 1. So if you imagine we have this point here, and let's do this at x equals 0. All right. So what are we going to have? We're going to have... So our Taylor series approximation is going to be... So the f of 0, so e to the minus 0 is going to be 1. Actually, let's not do this minus 1. Let's just do it itself. Erase that. All right. So we're going to do f of e to the minus x. So at 0 is e to the minus 0 is 1. So the value there is going to be 1. Plus the first derivative of it, this is minus e to the minus x. And the first derivative evaluated at 0 would be minus 1. So this would be minus 1 times x minus 0, which is 0. So that's minus x. Plus, we have 1/2. Second derivative is e to the minus x times e to the minus e to the minus x times minus e to the... Second derivative is e to the minus x. So second derivative evaluated at 0 is going to be 1. And then x minus 0 squared is x squared. So plus x squared. And from there it continues on, minus 1/6 x cubed plus ... All right, so that's e to the minus x. So if we want some approximation for e to the x minus 1, so e to the minus x minus 1 is approximately, so we'd take away the 1 there. So we could say that this is f of x equals 1 minus x plus, and then terms that depend on x squared or more. So this ox squared, order x squared, so that means that the next subsequent correction depends on x squared. So the x that's very small, x squared is going to be very, very small, so x squared won't matter. So if e to the x minus 1 is approximately x at x equals 0. So near x equals 0, we can approximate e to the minus x minus 1 as minus x. Sorry, need a minus sign there. You can approximate that as minus x near x equals 0. So this is useful in some things where e to the minus x minus 1 might be complicated, but minus x might be simpler to work with. So one last thing to note before we go is that a Taylor series at x naught equals 0 is called a Maclaurin series. So that Taylor series that we just did was a Maclaurin series because we were expanding around x naught equals 0. So a lot of times it is convenient to set things up in such that we're expanding around x equals 0, because as you see, a lot of the math of more complicated things canceled out and went away because we were at 0.